If you haven't already, please print this handout and we'll fill it in together. We're talking about concentration. And so we have to remember that this is just the quantity of a given solute in a solution. That's all concentration is a measure of. Basically, we always express it as a ratio of some sort that compares the quantity of the solute to the quantity of the solution. So the general form for any concentration is the quantity of the solute as a fraction of the quantity of the solution. And you're going to see there's a few different ways you can express that concentration numerically, but the basic idea is always the same. It's a ratio of the solute to the solution. And there's two other words that we use when describing concentrations. A solution can be dilute or concentrated. And when you set up your concentration as a ratio, comparing solute to solution, you're going to get a small number if your solution is dilute, and a big number if your solution is concentrated. So I drew some pictures just to the side here. That would be a picture of a dilute solution, and this one would be a concentrated solution. So the dots are supposed to represent the solute particles, and the box is the container that holds the solution. So just keep those ideas in mind as we go through the rest of this. Now I mentioned there's a few ways we can represent a concentration numerically. We can express it as a percent, which you see here. We can express it as parts per million or parts per billion. Maybe you've heard those terms used before. But the other way that we're going to look at is the one at the bottom, which is molar concentration. So we are going to go back and visit our friend the mole, and we're going to express concentration in terms of moles. So I'm going to show you how to calculate concentration three different ways. So if we look at percentage composite concentration, this is what you see on a lot of consumer products. So for shampoo, for example, you might see a percentage by volume of the main ingredient in your shampoo. So take a look at your shampoo bottle, and you might see a percent sign. You might see V/V. It would represent a volume by volume percent concentration. Or you might see a mass by volume or a mass by mass percent concentration. Basically, if your solute is a liquid and your solvent is a liquid, you're going to use a volume by volume percent concentration. If your solute is a solid, you would measure its mass. And if your solute and your solvent are both solids, you'll use a mass by mass percent concentration. And I have some examples that we'll go through later. But basically, here's the formulas. You can express the concentration as a percentage by volume this way. Take the volume of your solute, divide it by the volume of your entire solution. That'll turn it into a decimal, multiply by 100 to turn it into a percent. You can do the same thing if you have the mass of your solute and the volume of your solution, or if you have the mass of your solute and the mass of your entire solution. Now, things you have to remember: when you're doing this, it's important that you have the same units on the top and the bottom. So if you're doing a volume and a volume, they should both be in milliliters or both be in liters, or as long as they're in the same units. Same with mass. If you have both in grams or both in kilograms, then it'll work out. What you don't want is one of these in grams, the other one in kilograms. That would not give you an accurate percent by mass. For this one, we have a mass on the top and a volume on the bottom. This will work out if you have grams on the top and milliliters on the bottom, especially when you're dealing with aqueous solutions, because 1 gram of water is equal to 1 milliliter of water. So these units are pretty much the same, so that you can get an accurate percent concentration. The other one is parts per million, and this is really pretty much the same thing. You can think of percent as parts per 100, Now we're just doing parts per million or parts per billion. So instead of multiplying by 100 to get a percent per 100, we're going to multiply by a million to get parts per million, or a billion to get parts per billion. So it's the same thing. You represent your concentration as a ratio of the mass of your solute to the mass of your entire solution. That'll turn it into a decimal. Multiply it by a million to get parts per million, or by a billion to get parts per billion. A note about units. These are some alternative units to parts per million. So 1 part per million is equal to 1 gram per 1 million milliliters, or 1 gram per 1,000 liters, or a milligram per liter, or a milligram per kilogram, or a microgram per gram. All of those mean the same thing. But the big thing I want to talk about is molar concentration. So this is expressed as moles per liter. Remember from the last unit, we use moles to represent huge quantities of particles. We're going to do the same thing here. If you know the number of moles of your solute, you can use that to calculate the molar concentration. So the units are moles per liter. So you can see by the units what we're going to do to calculate it. We're going to take our number of moles and divide by number of liters of the solution. So there's your formula. C equals N over V. When you're doing this formula, when you're plugging numbers into that equation, it's important to put the proper units in. So you need to have moles on the top, and you need to have liters on the bottom. So if you know the milliliters, you have to change that to liters in order to do this accurately. If you flip the page over, we'll go through some examples. Okay, first one. A photographic stop bath contains 140 milliliters of pure acetic acid in a 500 milliliter bottle of solution. What is the percentage by volume concentration of acetic acid? So, percentage by volume, I take the volume of my solute, divide it by the volume of my solution, multiply by 100 to get my percent. So, volume of my solute is 140 milliliters, volume of my solution is 500 milliliters. They're in the same units, so that's good. And I'll just do my calculation. So once I do my calculation, I get 28%. Now just a note about communication. In brackets, you should write V/V to indicate that you used a volume for the solute and a volume for the solution. So this is called 28% concentration by volume of acetic acid. Next question, a sterling silver ring has a mass of 12 grams, contains 11.1 grams of pure silver. So this would be an example of a solid solution. What is the percentage by mass concentration of silver in the metal? Okay, well, we have the mass of silver, we have the mass of the solution. We can use our formula, plug in our numbers, and away we go. So after you do your calculation, you'll get 92.5% mass by mass of silver. So there's that notation again. You want to make sure you put that into your answers to indicate what you actually did to calculate the concentration. This next example deals with parts per million. So dissolved oxygen in natural water is an important measure of the health of the ecosystem. In a chemical analysis of 250 milliliters of water at, this just means standard ambient temperature and pressure. We'll get to that more in the last unit of the course. So we have 250 milliliters of water, 2.2 milligrams of oxygen were measured in that sample. So we have a mass in milligrams of oxygen. We have a volume of solution in milliliters. And we want to know what's the concentration of oxygen in parts per million. So I could figure out the mass of water in milligrams and then I would have the same units for the mass of oxygen and the mass of my solution. And I could plug in my numbers and multiply by 1,000,000 and get my answer in parts per million. So the conversion, remember 1 milliliter of water is 1 gram. So I can use that conversion factor. 250 milliliters is 250 grams, but I want milligrams. So just remember there's 1,000 milligrams in 1 gram, so if I have 250 grams, that's 250,000 milligrams. My units are now the same. Do my division, multiply by 1,000,000, it's 8.8 parts per million of oxygen. So that means for every 1,000,000 particles of my solution, 8.8 of them are oxygen. Okay, this next question's a little bit different. This time, we know the concentration. And I'm asked what mass of sugar is present in a 175 milliliter glass of that juice. So I'm going to start by saying, well, the concentration is equal to the mass of the sugar divided by the mass of the juice, which means this, 12% is 0.12, mass of sugar on the top, mass of the whole solution on the bottom, and we're using that conversion factor. 1 milliliter is 1 gram, so 175 milliliters is 175 grams. Do your algebra here. If you want to solve for the mass of the sugar, you have to do 0.12 multiplied by 175. So there's 21 grams of sugar in that juice. Okay, now we're going to deal with molar concentrations. So this question here, in a quantitative analysis, a stoichiometry calculation produced 0.186 moles of sodium hydroxide in 0.250 liters of solution. Calculate the molar concentration of sodium hydroxide. The formula we're using is C equals N over V. N is the number of moles. V is the volume in liters. So I plug in my numbers, moles and liters, and I get my answer of 0.744 moles per liter of sodium hydroxide. So what this concentration means is that for every liter of solution, there are 0.744 moles of sodium hydroxide in it. Last question. To study part of the water treatment process in a laboratory, a student requires 1.5 liters of 0.12 moles per liter aluminum sulfate solution. What mass of aluminum sulfate must she measure for this solution? So I have a volume, I have a concentration, but I'm asked for the mass. That's grams. So I'm going to have to do a couple different steps here. But I know volume, I know concentration, so I'm going to start with C equals N over V. I'm going to rearrange that to solve for number of moles, plug in my numbers, and find out the number of moles. So I have 0.18 moles of aluminum sulfate. I'm asked for the mass though. So this is where I have to remember my formula from the last unit, rearrange to solve for the mass, and I can plug in my numbers. This number is the molar mass of, remember, it's aluminum sulfate, so you would have to find out the chemical formula for that first, and then you should get this as your molar mass. Try that on your own, see if you get the same answer. If you don't, you can email me. But continuing on here, if we multiply moles by the molar mass, we will get a final answer of 62 grams of aluminum sulfate. So she would need to measure out 62 grams of aluminum sulfate and add that to her 1.5 liters of water, and that would get her the desired concentration.